You are listening to The Vocal Technologist. Spoken tech for your ears.
Inference takes up roughly 80 to 90% of an AI model's lifetime cost. Let that land.
Yeah, it's a brutal statistic. I mean, it completely changes how you have to look at the economics of this entire industry.
It really does. And if you're hanging out with a vocal technologist, we like to look past all that shiny marketing and, suss out what's actually running the show.
Right, getting past the press releases.
Exactly. So we are going to get into the guts of the data world. We aren't here to hype up the next big model release or whatever the internet is yelling about. We're looking at the hidden physical bottlenecks.
The stuff that actually matters.
Spot on. The infrastructure that prevents billion-dollar apps from completely crashing, and the genuinely awkward reality of why supposedly, smarter AI models are suddenly failing at just really basic everyday tasks.
Yeah, which is a massive headache for engineers right now.
Oh, I bet. And to figure this out, we've pulled together engineering blogs from Meta's latest storage white papers and some fresh benchmark data on time series AI.
Because the public narrative is, well, it's almost always about the software, right? People just obsess over the magic of the algorithm.
The magic black box.
Yeah, exactly. But when you hit a certain scale, the software is entirely at the mercy of the physical constraints. The hardware just sets the ceiling.
So if you're listening to this thinking the cloud is just some, airy, weightless magic, there is a massive physical toll to every single AI token generated.
Absolutely. I mean, let's actually walk through the life cycle of an AI token. Because the entire economic model of generative AI, it all comes down to a very specific metric, which is cost per token at a target latency.
Right. How fast and how cheap.
Exactly. And that generation process is split into two distinct phases, and they break the hardware in entirely different ways.
Okay, so the two phases. Walk me through the first one.
So first you have the pre-fill phase. This is when the model is reading and, digesting your prompt.
Like reading the instructions you just typed in.
Yeah, exactly. And this phase is entirely compute-bound. So the GPUs are just doing massive amounts of math as fast as possible to basically understand the context of what you just asked.
Okay, that makes sense. So pre-fill is just the heavy lifting, pure number crunching.
Spot on. But then, and this is then comes the decode phase. This is when the model is actually generating the response.
Yeah.
Spitting out the answer one word or one token at a time.
Right.
And this phase is entirely memory bandwidth bound.
Wait, hold on. Why does generating the text suddenly rely on memory bandwidth instead of just, doing more of that math?
Because every single time the model spits out a new word, it has to fetch the entire context of the conversation from memory all over again.
Oh, wow. Every single word.
Every single word, just to figure out what the next word should be. So the processors are actually just sitting there, literally waiting for data to be fetched from memory.
So it's not even about how fast you can do the math anymore. It's about how fast you can physically move the data back and forth across the chips.
Precisely. And this exposes the actual physical bottlenecks where the durable advantage sits. It's not just having, the smartest engineers writing code.
It's the actual plumbing.
Right. It's about HBM, which is high bandwidth memory. It's about NVLink fabrics, that's the physical plumbing, connecting the GPUs so they can talk without bottlenecks. It comes down to optics, the fiber cables moving the data, and fundamentally just the power grid.
That's the bit that absolutely floors me. I had this moment of genuine surprise realizing that the true ceiling of AI isn't some algorithm, it's the physical infrastructure.
It's physical copper and silicon.
Which is why you hear so much panic from engineers right now about things like KV cache management and quantization techniques.
Right. And for the listener who isn't, living in the back end every day, we should probably translate that. KV cache, key value cache, is basically the AI's short-term memory scratch pad.
Yeah, a temporary workspace.
And if you don't manage that efficiently, the model literally forgets the start of your prompt by the time it reaches the end, right?
Yeah.
Because it just can't hold it all in active memory. Exactly. It runs out of room.
And then quantization is basically just a brutal form of compression. Like it's intentionally lowering the mathematical precision of the model, so the file size is small enough to actually squeeze through the wires without choking the system.
That is a great way to put it. You're basically trading a tiny bit of intelligence for the physical ability to actually run the thing without breaking the bank.
It totally shifts the perspective for me. I keep picturing the AI cloud not as this invisible network, but as a massive hyper-stressed power grid. It's just vibrating with the sheer physical voltage required to fetch memory just to spit out, a recipe for banana bread.
It's a very accurate picture. And it leads to a massive structural problem. Because if decoding relies entirely on memory bandwidth, and high bandwidth memory is incredibly expensive, well, companies can't just buy infinite servers.
No, they'd go completely broke.
Exactly, so they have to get ruthless about where they store data.
Which is how we get to Meta's recent AI storage blueprint. Because I was looking at this, and it's a perfect example of this survival mechanism at scale.
It really is. I mean, Meta's architecture relies on a highly complex, multi-tier storage hierarchy. They don't just dump everything on the fastest, most expensive drives.
No, it cost a fortune.
A literal fortune.
Yeah.
So they use aggressive, intelligent caching layers. The hottest, most requested data is instantly available in RAM, while the colder data is pushed down to much cheaper, slower storage. And to make it work, they rely heavily on erasure coding.
Okay, I reckon we need to explain erasure coding because when I first read about this, it sounded like absolute witchcraft. I mean, it saves them heaps of money while keeping the data safe, but how does it actually work?
So traditional data protection is just replication, right? If you have a massive data set, you make 3 complete copies of it and just put them on different hard drives just in case one fails.
Which is incredibly expensive when you're dealing with, exabytes of data.
Right, paying for triple the storage. So erasure coding chops the original data into fragments, adds some complex mathematical equations to it, and spreads it out across the drives. So if a server dies, they don't have a clean backup copy waiting. Instead, they mathematically rebuild the missing pieces from the surviving fragments using those equations.
So they're basically using advanced calculus to avoid buying more hard drives.
That is exactly what they're doing, yeah.
That's brilliant. It gives them incredible durability, but uses a fraction of the physical disk space.
Yeah.
But it's not just the mega giants like Meta playing these storage games, right? I want to point to Grab.
Oh, Grab's a great example.
Right. They run this massive ride-hailing and delivery network across Southeast Asia, and they recently had to migrate their entire fraud counter service.
And just for context, the fraud counter service is their most critical database.
Yeah.
It's a high QPS, so queries per second system. Every single transaction, every ride booked, every meal ordered, it all has to be checked against historical patterns in real time to prevent fraud.
That was heavy.
Very heavy. And they migrated that from a wide column database over to an Aerospike NoSQL database.
And doing that on a live system that is actively preventing fraud is basically performing open heart surgery while the patient is, running a marathon.
Yeah, the stakes are massive.
If it goes down, the fraud gates just open, or legitimate customers can't book their rides. But they pulled it off with zero downtime.
The engineering behind that transition is honestly beautiful. They use storage facades and shadow reads.
Shadow reads are so clever. For anyone who hasn't seen this, that means the live system is routing the actual traffic to the old database to keep things running normally. But in the background, it's secretly sending the exact same read request to the new database, just to verify it actually works.
Yeah, testing it under real pressure.
It's like testing a backup parachute while the main one is still safely deployed. It doesn't impact a single customer.
Exactly. And they use deterministic traffic splitting to slowly dial up the load on the new database, going from 1% up to 100% with a config-driven rollback ready if anything spiked. But the real magic, the actual unlock, was the architectural shift. They moved from a Roper bucket storage model to Kerr counter-ordered maps.
Okay, this is the part that confused me at first, but once I got it, I realized this is where the actual money is made in tech. So think of the old Roper bucket system, like writing every single fraud attempt by a user on its own individual sticky note and just tossing it in a pile.
A very large, very messy pile.
Right. So to find a user's history, the system has to sift through the whole pile and read every single note. Massive disk usage, huge processing time.
Right, the record cardinality was just completely out of control.
So the ordered map is like switching to a tidy ledger. You have one page for one customer, and when they do something, you just update the tally on that single page.
Yeah.
It takes a fraction of the space, and it's instantly searchable.
Exactly. By switching to ordered maps inside Aerospike, they consolidated all that sprawling data into something highly efficient.
And the result was huge. They cut their P99 read latency, which is the absolute worst case wait times for a database query.
Okay.
They cut that by roughly 50%.
Wow.
And they slashed their per node hardware costs by 50% too. I mean, you don't need to build a new warehouse. You just reorganize the shelves so intelligently that you suddenly need half the forklift drivers to find the same boxes.
It's the perfect analogy.
I love pushing back on the industry obsession with, magic AI fixes, because this right here is the reality. It's brilliant, boring data structures.
It's the absolute foundation. But, there is a cruel irony to all this infrastructure work.
Oh, I know exactly where you're going with this. You get the storage sorted, you get the memory bandwidth humming, you plug in the absolute smartest new AI model, and then it completely fails at filling out a basic form.
Yes, exactly. The AI agent paradox.
It's wild. Now, before we pick apart why the smartest tools are suddenly the most useless at basic admin, if you're keen on untangling the real data like this, instead of just listening to the hype, chuck us a subscribe. It really helps us keep focusing on the actual guts of the tech. So, what is going on with Anthropic's newer models here?
Well, by every traditional benchmark, their newer models are definitively more capable. They solve complex reasoning tasks correctly, their logic is sound, they score higher across the board.
Right, they are objectively smarter.
Yes, but developers are finding that when they put these newer models into strict agent harnesses, so where the AI is supposed to trigger a specific company tool or fill out a rigid database schema, they fail far more often than the older models.
They fail by adding invalid fields, right? They just start making up extra parameters that the database immediately rejects.
Exactly. They get creative when they shouldn't. And the technical reason why is fascinating. It appears they have actually become overfit to Claude Code's highly forgiving tool format.
Okay, so we need to untangle why Claude Code is acting like a bad teacher here. What is it doing?
So Claude Code is Anthropic's own coding environment, and it's designed to be incredibly flexible. If the AI is writing code and it throws in, say, an extra thought process or an unexpected variable, the Claude Code environment just handles it gracefully.
It doesn't break.
No, it silently fixes the typos or ignores the extra fluff in the background.
Ah. So because Claude Code acts like this over-accommodating assistant, the AI never actually learns the penalty of breaking the rules. It gets sloppy because his training environment was just, well, too nice to it.
Yes, precisely. The model learns that it doesn't need to be perfectly precise to get a good outcome. But when a developer takes that same model and plugs it into a rigid corporate API that demands, say, exactly 3 fields, formatted perfectly, with 0 extra text, the model panics.
It spits out its usual sloppy output, the API completely rejects it, and the system crashes.
Yep, it falls over.
It's so funny to me. It's exactly like hiring a brilliant executive who is incredible at high-level strategy, but absolutely refuses to fill out their corporate expense form properly because they think they're, too smart for the template.
Oh, totally.
They just write lunch on a napkin, slide it across the desk, and expect accounting to just process it.
And accounting strictly rejects the napkin.
Exactly.
The implication here is massive for anyone building reliable AI agents right now. You simply cannot rely on the model to police itself anymore.
Right.
Developers are realizing they have to build incredibly strict schema validation or heavily constrained tool calls just to force the model into compliance.
So how do you actually rein in the stubborn executive? I mean, if the models refuse to behave naturally, how do you get them to do useful work without causing complete chaos in your databases?
This is where we get into the emerging discipline of context engineering.
Context engineering. I'll be honest, when I first heard that term, it sounded like a bit ordinary, like a shiny buzzword for just doing basic data hygiene. Is anyone actually making real money off this, or is it just consultant speak?
Oh, no, it's definitely making money. Context engineering is really shaping up to be the new analytics engineering. You know how we used to spend all our time writing SQL queries to structure data for human dashboards?
Oh yeah, heaps of time.
Well, now the goal is structuring company knowledge so that agents can answer natural language questions reliably.
Because if you just point an LLM at a raw data warehouse, it will hallucinate a total disaster.
Utter disaster. It'll confidently make up numbers. The biggest reliability gains right now, they don't come from tweaking the model's weights. They come from clean data models and solid documentation.
Which is the unsexy work.
It is, but it works. Teams are finding that taking the time to build a pristine semantic layer can take an AI agent from 40% accuracy to 90% accuracy.
Let's define semantic layer for a second, just so everyone is on the same page. If you don't have one, and the AI asks your database for the active user count, the sales department might define an active user as someone who bought something, right?
Yes.
While marketing defines it as someone who just opened an email. So the AI gets confused and just guesses. A semantic layer forces one mathematical truth across the whole company so the AI literally can't misinterpret the metrics.
Exactly. It's the single source of truth. Interestingly, the standard developer tricks like query logs and profiling don't actually add much value when you're debugging AI agents.
Really?
Yeah, it's all about the context you feed the model.
Yeah.
If the context is muddy, the output is wrong.
Okay, you said people were making money off this. Give me a real-world example where context engineering actually worked.
Vercel is a prime example of this working perfectly. They completely automated their SDR function, the field development reps who qualify inbound leads.
Okay.
They took a 10-person human team down to roughly 1.25 people managing the system.
Wow.
And they're claiming a massive 32x ROI. The whole automated setup cost them just $5,000 a year to run.
That is wild. From 10 people to basically one person supervising the code. How did they actually map that out without the agent hallucinating bad sales pitches to actual clients?
Well, they used a go-to-market engineering model. They paired a software engineer, a data scientist, and a domain expert, so an actual human sales rep.
Right.
They didn't just give the AI the CRM login and hope for the best. They documented the best practice workflows perfectly into the system, and then they ran the agent in shadow mode for a long time.
Ah, like grab testing the database with the shadow reads.
Exactly the same principle. They QA'd the AI's outputs against what the human rep would have done in the exact same scenario, tweaked the context, and then gradually removed the humans from the deterministic tasks once the accuracy was fully locked in.
Okay, but there is a massive catch here, isn't there? I mean, you can't just slap an LLM on top of a messy 5-year-old Salesforce instance and expect Vercel's results.
Oh, absolutely not. That would be a nightmare. This only works if you have highly composable APIs, that pristine semantic layer we talked about, an infrastructure that won't just blow up your cloud costs when you scale from 10 test queries a day to, 1,000 production scale agent workloads.
Because if the plumbing is bad, the agent fails.
The agent fails, or your AWS bill goes through the roof.
It translates perfectly to my favorite analogy for AI agents. They are basically highly confident interns. If you give a highly confident intern a perfectly organized, color-coded filing cabinet where everything is clearly labeled, they'll do a great job finding the answers.
Exactly.
But if you give that same intern a messy filing cabinet filled with loose, contradictory papers from 5 different departments, they'll give you a messy, hallucinated answer, and they'll look you dead in the eye while doing it.
That is exactly it. The model is just the intern. That context engineering is the filing cabinet, which, leads us to the physical reality of those filing cabinets and where this technology is bleeding into the future.
Right, because if we're building these perfectly organized filing cabinets, we need to know what they're actually built out of. So let's untangle the vector database showdown. It feels like everyone is fighting to be the core memory bank for these AI agents right now.
There was a massive benchmark comparing the leading open source vector DBs recently. And the big takeaway is that there is no single winner. It entirely depends on the mechanics of your specific workload.
So it's about picking the right tool for the job.
Exactly. Redis, for example, takes the crown for ultra-low latency and high QPS on hybrid search workloads. So if you need answers in absolute milliseconds, Redis wins.
But we should probably explain why Redis wins there. It's because it operates entirely in RAM, right? It's lightning fast, but it's volatile. Like, if the power drops, the memory drops, but for instant retrieval, you just can't beat physical memory. What about the other options?
Well, if you're doing complex filtering based on rich metadata alongside your vector search, Qdrant and Weaviate excel there. And if you're dealing with absolutely massive scale, I'm talking billions of vectors, Milvus is the architecture built to handle that kind of weight.
And again, the mechanics really matter here. Milvus handles billions of vectors without crashing because it physically separates the storage from the compute.
Right.
When you throw a massive query at it, it isn't trying to process the math and store the data on the exact same chip, which is what prevents the whole system from choking under the pressure.
Exactly. It's smart architecture.
Oh.
So the tools for storing the context are maturing rapidly, but the models themselves are pushing into spaces where they don't even need as much hand-holding from external databases.
Right.
I want to talk about time series LLMs.
This is a fascinating leap. I was looking at this new open weights model called Chi0 Alpha. It's a probabilistic time series forecaster.
And it is incredibly small compared to the big language models. It's only 102 million parameters.
Tiny but highly specialized. So instead of predicting the next word in a sentence, it predicts the next number in a sequence.
Right. It patches data into 32-step windows and uses a causal transformer to predict future values. But here's the critical part. It predicts quantiles.
Which means it doesn't just give you a single guessed number. Like if you ask it for next month's sales, it doesn't just confidently say 10,000. It gives you a calibrated probabilistic range.
Yes, it gives you the odds. It essentially says, I am 90% sure the sales will be between 8,000 and 12,000. And in testing, this tiny model beat almost every classical baseline forecasting method out there.
It only lost to the seasonal naive baseline on exactly 1 out of 97 task configurations. And
Yeah.
just to clarify for everyone, the seasonal naive baseline is literally the most basic forecasting method possible.
It really is.
It's just looking at what happened last December and blindly guessing that the exact same thing will happen this December.
Right, it's the absolute basic control. And TO alpha destroyed almost everything else. That means strong zero-shot forecasting is essentially here.
Zero shot, meaning you don't even have to train it on your specific company's historical data first to get a good result. It just looks at the raw numbers provided in the prompt and already knows how to predict the mathematical pattern.
Exactly.
So for you, sitting at your desk, running supply chain, does this mean you can finally ditch your dodgy Excel forecasting sheets?
Well, I would temper the excitement just a little bit. The baseline capability is there, yes. But real production value in forecasting won't come from just tweaking transformer architectures to be slightly smarter.
What's the holdup?
The real value is going to come from having strictly calibrated, probabilistic outputs and implementing really aggressive leakage controls.
Ah, right. Leakage controls being the guardrails that ensure the model isn't accidentally peeking at future data during validation and just, cheating on the test.
Exactly. It requires strong routing and ensembling of different models. You can't just plug TO alpha into Excel and fire your supply chain manager.
It always comes back to the engineering wrapped around the model. Looking at everything we've pulled apart today, from the sheer physical voltage required to generate a single token, to Grab reorganizing their data to have their storage costs, to agents needing perfectly clean semantic layers to even function.
It's all connected.
It is. My staked prediction is this. The defining factor for the next decade of tech won't be who has the absolute smartest AI model. It's going to be who has the cleanest, most ruthless data plumbing to feed it.
I completely agree. The infrastructure is the destiny. The models are really just the engine. But the data plumbing is the transmission, the chassis, and the wheels.
Which leaves a massive question hanging. If data plumbing becomes the real moat, do the big tech companies even need to build the best AI, or do they just need to own the only pipelines wide enough to run them? If you want to untangle more of this with us and keep clear of the hype, you can find us over at vocaltechnologist.cu. That is spelled .ci-play-o-o-u. Vocal Technologists, see you soon.
Spoken Tech for your ears.